Okay, so we're asked about Chebyshev's theorem and the empirical rule. So here's the question. Loretta, who turns 80 this year, has just learned about blood pressure problems in the elderly and is interested in how her blood pressure compares to those of her peers. Specifically, she's interested in her systolic blood pressure, which can be problematic among the elderly. She has uncovered an article in a scientific journal that reports the mean systolic blood pressure measurement for women over 75 is 131.4 mmHg. Assume that the article reported correct information. Complete the following statements about the distribution of systolic blood pressure measurements for women over 75. So according to Chebyshev's theorem, at least what percentage of the measures lie within 2 standard deviations of the mean? And then suppose that the distribution is bell-shaped if approximately 68% of the measurements lie between 125.3 and 137.5 mmHg, then the approximate value of the standard deviation for the distribution according to the empirical rule is blank. So there's 2 rules here which are kind of related and kind of not. So the first is this Chebyshev's theorem. So what Chebyshev's theorem says is so let's write his name first. So what that theorem says is, hey, in any kind of distribution of data, whether it looks like a bell or not, at least 1 minus 1 over k squared portion of your data will be within k standard deviations. Okay, in any distribution. That's pretty important. So here, if we're using Chebyshev's theorem, we want to know how much of the measurements will lie within 2 standard deviations. So here, k is equal to 2. So we'll do 1 minus 1 over k squared, which would be 1 over 1 minus 2 squared, which is 1 minus 1/4, which is 3/4. So we would say at least 3/4 of the data, no matter what kind of distribution it is, at least 3/4 of the data will be within 2 standard deviations from the mean. Now, if you want to change this to a percentage, let's just make sure we do that. So 3/4 in your calculator is 0.75. And if you want to change it to a percent, so this is fraction, decimal. If you want to change it to a percent, you're going to take the decimal times 100 and tack on the percent sign. So you would have 75%. So now the second part of the question says, suppose that the distribution is bell-shaped, which is important. Bell-shaped curves and bell-shaped distributions have special properties. So if approximately 68% of the measurements lie between 125.3 and 137.5, then the approximate value of the standard deviation for the distribution, according to the empirical rule, is blank. So there's 2 things that are really important here. The distribution is bell-shaped, and we're using the empirical rule. So let's just review that empirical rule real quickly. If you have a bell-shaped curve, so empirical rule, so the empirical rule says that in your bell-shaped curve, the center is the mean, right? The mean's the highest point. It's also going to be the same as the mean, the median, and the mode. If we jump between 1 standard deviation, so let's call the mean x with a little bar over it, then if I move to the left, one standard deviation, moving to the left subtracts. So this bar here would be x bar minus s. And if I move right s, then this second bar would be x bar plus s. So the empirical rule says 68% of your data is in there. Now that's really all we need for this particular problem, but let me just give you those percentages anyway. So if I move left another standard deviation, that means I've gone left one standard deviation to get to the orange bar and a second standard deviation to get to this blue bar, then that value would be x bar minus 2s. And with the same idea, if I move right one more standard deviation over here, this bar would be at x bar plus 2s. And what the empirical rule says there is that 95% of the data will lie in between. So starting from x bar minus 2s, going all the way over, that will be 95% of your data. And then we really only count up 3 standard deviations away. So let me just change my color here. We'll go green. If I go one more standard deviation to the left, that would be x bar minus 3s. And on the other side, if I went one more standard deviation to the right, that would be x bar plus 3s, because it's a third standard deviation. And the empirical rule says that between x bar minus 3s all the way to x bar plus 3s, that will be 99.7% of your data will be in between the mean subtract 3 standard deviations to the mean plus 3 standard deviations. So that's the term within 3 standard deviations. So now this problem is a little bit backwards, because most of the time the empirical problem will be like, hey, what percent lies between these two values? This guy says, hey, it's bell-shaped, and I know 68% lie between 125.3 and 137.5. So what we want to do is find that standard deviation. So let's draw the picture again, but we're going to use numbers here. So the center is going to be at the mean, and then we care about 125.3 and 137.5. Now, the problem told us what the mean was, but let's pretend that we didn't know the mean. One feature of your bell-shaped curve is that it's symmetrical, which means if 50% of the data is on this side, then the other 50% would be on this side. So it's perfectly symmetrical. So if I've got these two values, 125.3 and 137.5, that mean is going to be right in between there, because it's an empirical rule problem. If it's just random numbers, it's maybe not right in the center, but for an empirical rule problem, because the empirical rule has symmetry in it, we could just find the middle by finding the average. So we would find the exact middle of these two, which would be 125.3 plus 137.5 divided by 2, which does make 131.4. So we know this guy here is 131.4. So that's the middle, and that's going to be important. So the second thing that was really important was the fact that it had 68%. So because it's 68%, we know that each one of these bars is going to be 1 standard deviation away. So if I plus a standard deviation from the center, I get 137.5, and if I minus a standard deviation from the center, I should get 125.3. Sorry, that was my 3-year-old. So if we could find out how far it is to go from the center to one side, that would be the standard deviation. Because it's 1 standard deviation away, I know that x bar plus 1 standard deviation would make 137.5. But I know x bar is 131.4. So 131.4 plus s equals 137.5. So I can subtract 137.5 minus 131.4, and that gives us 6.1. So now, to check your work, you can find the second standard, or not the second standard deviation, but the other place over here, this 125.3. I know that x bar minus s should equal 125.3. And what we decided was x bar was 131.4, and we think s is 6.1. So we do that subtraction in your calculator, and you do, in fact, get 125.3. So what does that mean? That means that these two were within 1 standard deviation of the mean, and the standard deviation was 6.1.